Hi guys, so in this video we will start looking at the scheduling routine algorithms. So these algorithms are what actually controls how processors are picked from the ready queue and are sent to the CPU by the low level schedulers. So this is the underlying fairy dust or the underlying algorithm or the magic that actually does that. Let's start. Now there are four main scheduling algorithms. The first algorithm is called first come first served. Second algorithm is called shortest job first. Third algorithm is called shortest remaining time first. And last algorithm is called round robin. Now, these words or terms, writing them in full form might be quite tongue twisters. So therefore, first come first serve is summarized as FCFS. Shortest job first is referred to as SJF. And shortest remaining time first is referred to as SRTF. Right? Okay, round robin, of course, you can refer it to as RR, but let's just refer to it as round robin. It's not as complicated as the rest. And again, the operating system and the processors themselves would determine which scheduling algorithm to use. So therefore, we are going to learn about all four of these in our syllabus, but remember only one of these will ever be used by a given low-level scheduler. One or combination, but it's just going to be a single scheduling algorithm. There might be other algorithms that we don't have in the syllabus, but we are only going to learn about these four. Only one of these or two of these or three of these in conjunction together will be ever used by a low level scheduler. Now, to understand scheduling, I will look at 5 dummy processors. Basically, I will give myself 5 processors, process A, B, C, D and E. I'll give my processors a burst time and arrival time, and then look at how each of these scheduling algorithms work given these 5 processors. Is that clear? So I'm just going to start off with some 5 processors that are going to come to the ready queue and are going to be taken into the CPU. We will look at how these 4 algorithms treat these 5 processors differently. Now let's look at process A. The process A has a burst time of 45 milliseconds. What does that mean? If you remember, what that means is that process A would occupy 45 milliseconds in the CPU to finish executing. But remember, depending on the algorithm, if it's a non-preemptive algorithm, what does it mean? Process A can finish executing before the next process is taken place. So the CPU will be allocated process A 45 milliseconds in one go. But if it's a preemptive scheduling algorithm or a preemptive system, would it be occupied 45 milliseconds in one go? No, right? It's allocated a particular time quantum. So it's like a patient that needs 45 milliseconds of time from the doctor, which is our CPU in this case, but it doesn't get 45 milliseconds in one go. It will be given maybe 5 milliseconds today and then the remaining 5 milliseconds later. So it depends. So burst time nonetheless is the time it takes for the process to execute in the CPU. Arrival time, if you remember, is the time that these processes arrive. So process A arrives in the ready queue at 0 milliseconds, the second process at 8 milliseconds, 10 milliseconds, 14 milliseconds and 90 milliseconds. So this is the arrival time of this process to the ready queue, and this is the time it takes for the process to execute in the ready queue, in the processor, I'm sorry. So we have understood what these processes are. Now it's time to just look at the algorithms. Before that, there's just one additional thing I want to teach you. Average waiting time is something that we calculate for every single scheduling algorithm. It is the sum of waiting times of individual processors divided by the number of processors. And the idea is we are trying to find an algorithm that has the least waiting time out of everything. Is that clear? So hopefully that makes sense to you. If I said waiting time, beg your pardon, what I meant is average waiting time. So we're trying to find an algorithm that has the least average waiting time. Although one process might have large waiting time, overall all processors might have an average of very little waiting time. So we're trying to minimize the average. Okay, let's dive in to the first algorithm, first come first serve. Now first come first serve algorithm works just like a normal queue. What does that mean? A process arrives at the ready queue and they are admitted to the processor based on their arrival time. So basically the process that arrives to the ready queue first is the process that is taken into the CPU first. That's all. So it's a first come first serve basis. Processors added to the ready queue first leave the ready queue first. So basically how a queue works, right? What does it mean to leave the ready queue? It means that it's going to be leaving the ready queue to the processor. So if you remember the definition of non-preemptive, FCFS is a non-preemptive algorithm. Each process is allocated the CPU until it terminates. Any processes that are arriving earlier have to wait for that other process to finish. Okay, now shall we actually execute this and see what the ready queue will look like for an algorithm like this? Amazing stuff. Okay, so this table will help us understand this very easily. At time 0 milliseconds, process A arrives. Okay, remember in this diagram I said that process A's arrival time is 0 milliseconds. So at 0 milliseconds, process A arrives. And as soon as process A arrives, the first come first serve algorithm that is running in the low level scheduler will send the process A to run in the CPU. Done. But then at 8 milliseconds, process B arrives. Okay, at 8 milliseconds, process B arrives. But remember, process A will take 45 whopping milliseconds to finish executing, right? So even though process B arrived at 8 milliseconds, can it go to the CPU until process A finishes? No. It will have to wait until this entire 45 milliseconds are over for the next process to take place. So what will happen? Process B arrives at the ready queue, but it must wait. Process A is still continuing. And then at 10 milliseconds, process C arrives. Again, why 10? Because that's the arrival time I stated for process C. So process C arrives but waits, PA is still continuing. Then at 14, process D is arriving, but it has to wait since PA is still doing. Then at 19, process E arrives, but it still is waiting because process A is continuing. So this is basically like a guy that is at a cashier, has like 100 items. The cashier's queue is getting filled up more and more and more, but can any of the other people go to the cashier until that 100 item guy finishes billing his items? No. This 100 item guy is like process A. It's waiting. All other processes are waiting for process A to finish, and only then can they go in. At 45 milliseconds, finally, this damn process finishes. Process A terminates. But then, soon after that, what is taken in? Process B. Process B is taken in, but all the other processors still have to wait. So think about a supermarket queue. This 100 element or 100 item guy goes, but then the next item guy comes, right? The next process comes, and the other processors or the other people at the cashier have to wait. At 63 milliseconds, process B terminates. If you are worried about how these values are calculated, basically 45 is the so-called burst time of process A, right? 45 plus 18. Basically, once process A terminates, process B will be immediately taken in. So process B will take 18 milliseconds of the CPU to execute. So whatever time it was taken in plus 18 will be the time it ends. So 45 plus 18 is 63. So process B terminates at 63 milliseconds. Then PC runs process C. Then that terminates at 68. It terminates. Then D is taken in. Then D terminates. E is taken in. And finally, E terminates at 102 milliseconds. So this, ladies and gentlemen, is what the ready queue looks like for this system. Process A arrives, finishes at 45 milliseconds. Then process B arrives, finishes at 63 milliseconds. Process C arrives, finishes at 68, finishes at 91, and finishes at 102. Okay, so let's ask ourselves, what is the average waiting time for each of these processors? Process A Did it have to wait? Did it have to wait for it to be taken into the CPU? No. Since process A arrived first, it was taken in immediately. So the waiting time for process A is 0. What's the waiting time for process B? Process B was taken in only after process A finished. So its waiting time is 45 milliseconds. Process C's waiting time is 63 milliseconds because it is waiting for process A and process B in total time. Then process D is waiting for process A, B and C, that's 68 milliseconds in total. And process E is waiting for a whopping 91 milliseconds. Process A, B, C and D to finish. You divide all of that by 5 because you had 5 processors in total, and you can calculate that in this algorithm, these 5 processors have taken an average waiting time of 53.4 milliseconds. So each process did nothing for 53 milliseconds. That's absolute trash. Not good. But that's first come first serve. Pretty simple to understand. All you need to do is just understand a processor's waiting time by looking at its arrival time and its burst time and calculating the average accordingly. Hopefully this made sense to you. If you understand this, you're in good hands. We can move on to the next algorithm, which is shortest job first. Now in shortest job first, if you look at what for shortest job first means, you'll probably understand that it doesn't take in a process as soon as it arrives. It waits for the shortest job to arrive and then sends that guy along to the CPU. So let's see. In this algorithm, processors are added to the ready queue based on their burst time. Shorter processors are added first. SJF is non-preemptive. What does that mean? Just like first come first served, each process is allocated the CPU time until it terminates. Any processors that arrive earlier are queued. Okay, let's get this guy sorted with. Okay, so at time 0000 or 0 milliseconds, ask yourself, what process arrives? Now, if you think about what process arrives, you'll find shortest job first pretty confusing. Because process A is what initially arrives to the ready queue. So as far as the ready queue or low level scheduler knows, process A was the shortest it saw. None of the other processors actually arrived at the CPU at that time. It didn't see any of the other processors. At that time it only knows about process A. So process A is the shortest technically at that point of time. So it should take in that guy, right? No, it should take in that guy. So the idea is, I want you guys to keep the arrival time out of the door when you understand shortest job first. When you want to understand shortest job first, only ever consider burst times. You can imagine that all processors are sort of already there in the ready queue. Now, once they are already there in the ready queue, you don't have to worry about, so-called arrival times. They're already there. So they've already arrived. What happens is the shortest job first algorithm picks the right one, that is the shortest one first, and then sends it to the CPU. So at time 0, all processors are there. But ask yourself, which of these 5 processors runs in the shortest time? If you look at the table above, which of these 5 processors has the shortest burst time? Process C, right? So therefore, in the shortest job first algorithm, process C will execute first. And then after 5 milliseconds, it would have finished executing. And then what's remaining is PE, PB, PD and PA. Process E is the next shortest, and then process E executes. So likewise, process B would execute next because it's the next shortest. And then process D would execute. And then finally, process A would execute. So it's sort of like a cashier that looks at all the people in the queue, takes the guy that has the smallest number of items first, and leaves the guy that has 100 odd items last. So if you look at this, first come first serves total time and shortest job first total time it took is the same, 102 milliseconds, right? The total burst time for all the processors are constant, no? But what we're interested in is not the total time it takes, because that will be the same, the average time. So in shortest job first, the shortest job first, meaning the shortest job or the shortest process goes into the processor first. So therefore, PC goes in first, then PE, then PB, then PD, then PA. So let's calculate their waiting times. PC wasn't waiting for any time, so its its waiting time is 0. PE on the other hand was waiting for PC to finish, so its waiting time is 5 milliseconds. PB, the next process, would be waiting for 16 milliseconds for both PC and PE to finish. Then PD would have waited for 34 milliseconds and PA would have waited for 57 milliseconds. If you divide that by 5, you will see that it's so much better than first come first serve. It's now such that each processor's average waiting time is 22 milliseconds only. We sort of cut down this initial value almost by half, actually less than half. That's shortest job first. We don't give a damn about arrival time. Just look at their burst time, send the one that has the shortest burst time first, and the next processors follow. Alright, next comes, in my opinion, the hardest one. Shortest remaining time first, or SRTF. Now, this algorithm, I want you guys to pay attention very carefully. In the shortest remaining time first algorithm, guys, it's basically just like first come first serve, but there's a small difference. It operates just like first come first serve initially, but let's say while the first arrived process is taking place, let's say a smaller process arrives. Let's say a smaller process arrives in the queue. Then how the shortest remaining time first algorithm works is, it would tell the current process to wait and then take the shorter one and execute that instead. Now let's try and understand this with an example. We know that the shortest remaining time first algorithm's job is, it would take whatever arrives first, but if a shorter guy comes along, meaning a process that takes less time to execute, it will sort of preempt or tell the current process to go back to the ready queue and wait until that shorter guy finishes executing. Right? So let's read this just to understand this a little bit better. However, of course, let's start from the top because that's easier. In this algorithm, processors are added to the ready queue based on their arrival time. However, when a process with a shorter burst time arrives, that is a process that will take less time to execute, the current process is preempted. What does preempt mean? If you remember, preempt means to send a process back to the ready queue for some time. The shorter process is executed first, and once that process terminates, the next shortest process is taken in. So the process that was preempted might not have a guaranteed chance to come back immediately, right? But whatever next shortest process is taken in next. SJF is a preemptive algorithm. The previous two we studied were non-preemptive. This is preemptive because processors are interrupted with the arrival of shorter processors. A process cannot finish executing in one go. Let's look at this diagram first. In this table, at time 0, process A arrives and process A finishes running. Or does it? No, it does not. Process A arrives and process A runs. Okay, and then soon after while process A is running, at 8 milliseconds, process B arrives. Remember, the arrival time of process A was 0, but then its burst time is 45 milliseconds. So while that 45 milliseconds are being executed, process B comes along at 8 milliseconds of time. So what happens at 8 milliseconds? Based on this algorithm, since process B's burst time is less than process A, if you look at the burst time of process B's burst time is 18, whereas process A that is currently being executed is 45. So what this algorithm does is, it sort of gets excited when it sees a process that's executing or going to execute in less time. So what it does is, process A is running, but as soon as process B arrives while process A is running, it checks and sees whether process B is shorter than process A and realizes, yes, process B is shorter than process A. So then process A is preempted back to the ready queue and process B runs. So remember, process A runs from 0 to 8 milliseconds, but technically it should have been given a total of 45 milliseconds. But in this algorithm, what happens is, since process B arrived, which was taking less time than process A, what happens? Process A is preempted and process B starts running from 8 to 10 milliseconds again. What happens at 10? Now, shouldn't process B be given 18 milliseconds? No. Why? Because while process B is taking place, process C arrives at 10 milliseconds. So what happens? Although process B started executing at 8, process C arrived at 10 milliseconds. And what happened? Since process C arrived at 10 milliseconds and process C was shorter in burst time than process B, then process B is preempted and process C starts running instead. Now, while process C is running, which takes 5 milliseconds of burst time, process D arrives at 14 milliseconds. So technically process C should preempt itself, right? But does that happen? Process D is actually longer in burst time than process C. So based on this algorithm, what happens? Process C will continue because it's shorter than process D, and process D will wait. And then at 15 milliseconds, just 1 millisecond later, process C finishes. It's done. And then the process low level scheduler checks which of the remaining processes in the ready queue is shortest. It finds out that process B is shorter than process D, which is shorter than process A. So the next shortest job, which is process B, runs next. But then while process B takes place at exactly 19 milliseconds, by the way guys, if you are worried about where these millisecond values come from, you can always refer to the table above. Just go back to the video where I showed you the table and refer to it. So while process B is running, process E comes along, and then the computer determines the process E's burst time and process B's burst time and realizes process E is actually shorter than process B. So process B is preempted for the second time. Bad luck for process B. And process E takes place instead. So process E takes place for the remaining 30 seconds or 30 milliseconds. And then at 30 milliseconds, process E terminates, it's done running. And then process B starts running because, again, based on what's left in the ready queue, process B is the shortest. Process B runs for until 42 milliseconds. Then finally this guy gets to terminate. Then what's remaining in the ready queue? D and A. D is shorter than A. Then D runs. And then finally A runs once D terminates. And it will finish off in 102 milliseconds. Now the average waiting time for this algorithm is calculated in a different way. Now look at process A, guys. Process A entered at 0 milliseconds. So at the initial point, it wasn't waiting, right? But then at 8 milliseconds, process A, what happened? Could it continue processing? No. It was preempted, sent back to the ready queue. And from 8 to 65 milliseconds, it was actually waiting. And only then was it taken in back to the CPU. So to calculate the waiting time for process A, you have to do 65 minus 8, which is 57 milliseconds total waiting time for process A. Then for process B, what's process B's waiting time? Process B arrived at 8 milliseconds. Right? So at that point it wasn't waiting. But at 10 milliseconds, what happened to process B? It was preempted because a shorter guy came along. And then from 10 to 15 it was waiting. Process B is waiting. But then soon after, at 90 milliseconds also, what happened? Process B had to wait until process E finished. So this is another waiting time for process B. PB is waiting. Then finally it finishes executing at 42. So here there is two waiting times. One from 10 to 15 and another from 19 to 30. So it will do 10 minus 15 plus 30 minus 19, which is a total of 60 milliseconds of waiting time for process B because it was preempted at two different locations. And then process D. What's up with process D, guys? Process D was not preempted at any point. It got in and got out in one go. So process D's waiting time is 0. Very lucky guy. Then process, oh, did I talk about D? I'm so sorry, guys. It's not process D that was not preempted. It's process C. I forgot about C altogether. C arrived, got the CPU and finished executing in one go. So again, process C is what didn't have any preemption. So its waiting time is 0. Now process D. If you look at this diagram, you might notice that process D isn't getting preempted at all. But then it is actually waiting. Remember, process D arrives at 14 milliseconds. But if you look at the diagram, does it enter the CPU at 14 milliseconds? No, right? It only got the opportunity to get into the CPU at 42 milliseconds. So from 14 to 42, it was waiting, although it's not visible in this diagram. So for process D, the waiting time is 42 minus 14, which is 28 milliseconds. Then process A, guys, okay, sorry, not process A, process E was another lucky guy. Process E basically arrived at 19, got in at 19, and finished at 30. So it wasn't waiting any time. So process C and process E were very lucky. But overall, if you add these up and divide by 5, you'll get 20.2 milliseconds. So this is the most complicated algorithm. But you'll understand that this algorithm actually has the shortest average waiting time out of the remaining algorithms, right? Pretty successful. But what you need to understand is this statement here, that it's basically operating just like first come first serve, but when a shorter process comes along, it will preempt the current process, execute the shorter one, and then look at the next shortest process. So what it's doing is it's calculating what processors have the shortest remaining time and taking them first. And the last algorithm we will discuss for this syllabus is the round robin scheduling algorithm. Round robin we already discussed, I believe, in the first video in this series. So hopefully you should have an idea about what this is. In round robin, it's a preemptive algorithm, which means that each algorithm or each process is allocated a fixed unit of time known as a time quantum, right? So basically it's like doctor's appointments. A process comes, it gets some time, either it finishes in that time or it goes back to the ready queue and gets another time. So that's the idea, guys. So in round robin, a fixed unit of time is allocated to each process. Initially, the process is at the head of the ready queue, which is then allocated to the CPU. So the first process that arrives and is at the ready queue goes to the CPU first. So first come first serve there, but it will only get one time quantum. Now time quantum isn't a unit of measurement. Time quantum is just a sort of arbitrary unit which refers to some constant time set by the operating system. So one time quantum could be 5 milliseconds or 10 milliseconds or whatever, right? But it's just an arbitrary unit that refers to however many constant time units you allocate for each process. Now, however many time quantums or however much time you take, that time is referred to as one quantum. The first process that comes along to the queue is allocated time in the CPU for one quantum. And then once the time has elapsed, it is placed in the blocked queue and the next process in the ready queue is executed. Now, when this happens, guys, a process comes into the CPU, goes into the blocked queue. Process comes in, goes into the blocked queue. It cannot finish executing in one go, no? So the CPU has to constantly remember what each processor's previous results were. So for example, maybe process A executes for 1 millisecond, then soon after that process B might execute for 1 millisecond. But if process A happens to come back again for another time interval, it can't restart processing process A from the beginning. It needs to remember what was previously processed and start from there. So the process of saving the state of preempted processors so that it can be restored when they are entering back into the CPU is called context switching, which is a process used to save the state of preempted processors. Remember, this word is very important, guys. For the following example, let's consider that the time quantum is 5 milliseconds. Let's imagine what happens. In this diagram, process A arrives first. Process A gets exactly 5 milliseconds in the CPU. But then what happens? At 5 milliseconds, has any other process arrived at the CPU? No, right? The next process, process B, arrives at the CPU at 8 milliseconds. So when the first process A's time quantum of 5 milliseconds is over, there's no processors that have actually arrived at the ready queue. So it will allocate itself 10 more, or it will allocate itself one more time quantum of 5 more milliseconds. But then at around the 8 millisecond mark, process B arrives at the ready queue. But is it taken in immediately? No. It waits for process A's preemption to take place once it finishes its time quantum, and then process B executes for 5 milliseconds again. Remember, each process is only taking place for 5 milliseconds. And then what happens is process C happens to arrive at 10 milliseconds. So the idea is, guys, at 10 milliseconds process B arrives. At 8 milliseconds process B arrives, so it's taken into the process processor first, and then process C arrives at 10 milliseconds. But process B is already executing, so process C has to wait. So then process C executes for 5 further milliseconds, then process D executes for 5 further milliseconds, and you'll realize that this process continues. Whoever's first in the queue will go into the processor and allocate itself exactly one time quantum. But notice, at this point, process E is taking a very short amount of time. If you realize, process E's burst time is exactly 11 milliseconds. So if you think about it, looking at this diagram, guys, process E allocated itself 5 milliseconds here, another 5 milliseconds here, so altogether 10 milliseconds already gone. So what it needs is just one more millisecond. So even though the time quantum for each process is 5 milliseconds, if a process manages to finish before that, it will be preempted early. And you'll realize that this goes on for every other process as well. This table shows you every single change that takes place in this diagram, so you can go through this in detail. So if you guys want, you can take a look at this diagram, take a quick screenshot and observe the changes. But overall, you can follow a rule similar to what we did earlier to calculate the waiting time for each process. Basically, how much time is the process waiting without actually executing. And here, the average waiting time has actually increased to 39 milliseconds from the SRTF method. So it's not actually a better method right now, but we'll see how to improve this. Round robin is very flexible. Now, round robin's flexibility is entirely dependent on the time quantum. If the time quantum is too large, meaning if the time allocated to a particular process is very large, its efficiency becomes similar to that of first come first serve, right? The processors might finish early, so it's basically like first come first serve, right? But if the time quantum is too small, if processors are given like, let's say, 1 millisecond time quantum, what will happen? Every process will be context switched very quickly. So context switching also cannot happen at like such high rates. So the context switching overhead will be too high. The process will have to do a lot of work remembering what the previous process was and saving current processes back into the process control block and reading it back and forth, which takes a lot of time. So you need to choose like a Goldilocks value, which is between the largest and smallest time quantum. But hopefully you guys understood the different scheduling algorithms, which were first come first serve, shortest job first, shortest remaining time first, and last but not least, round robin. In the next video, we will discuss about CPU modes, interrupt handling, and most importantly, memory management. See you in the next one, guys. Bye bye.